Friedman, his father, Dr. Michael Friedman, his brother Raymond Friedman, his sister Kaylee Friedman, along with Austin Kissinger, and his brother Ryan Friedman. Let's welcome them all here today. Evan is a lifer here at Prep. He's been with us since preschool. From his days in the lower school to when Evan heads off to Georgia Tech next year, where he'll study computer engineering, that's a lot of time that's passed. But ask any of our seniors, and some may say it feels like it all just flew by, while others may say it felt like an eternity. Just looking at the last 4 years, Evan has participated in our varsity clay shooting team, our varsity soccer team. He's been a member of the National Honor Society since 10th grade. Since last year, he's been a part of the Honor Education Council, where he now serves as the vice president. And all of that is just in high school. Whether you've been at prep from preschool or not, think to yourself how much life you've lived since preschool. Does it feel like it's all flying by? We perceive time in different ways, and Evan is here to explain how that works. Please welcome Evan to the podium.
Thank you, Mr. Mims, for the wonderful introduction and for being an amazing advisor throughout high school. I would also like to take this opportunity to thank my family, and especially my parents, for always supporting me and for always being there for me. Finally, I would like to thank my group of friends for always keeping things interesting and for the many memories. Today I am going to talk about time and how both our concept of it and our measurement of it have changed over the years. To begin, we must define what time is, so I brought this question to my classmates for an answer. Hank said very philosophically, the passing of moments in the universe. Hadi stated fittingly, time is money, and Jackson said a series of moments compiled together. Now, for a more formal definition, the Merriam-Webster Dictionary defines time in 2 ways. Firstly, as the measured or measurable period during which an action, process, or condition exists or continues. And secondly, as a non-spatial continuum that is measured in terms of events which succeed one another from past through present to future. Before the modern world of universal time standards, ancient civilizations had many creative ways of tracking time. For much of history, the most common method of keeping time revolved around the motion of the sun. One of the earliest known timekeeping devices, the sundial, works by tracking its shadow across set markers to measure the sun's progression. However, this device has its limitations, as it is obviously useless when the sun is not visible. This limitation led to the later inventions of timekeeping devices, such as the hourglass, the water clock, and the candle clock. The water clock, first used circa 1400 BC in Egypt, works by having a constant flow of water into or out of a vessel. Then, based on the amount of liquid measured, the passage of time can be calculated. An hourglass, which many of us are familiar with, uses a narrow neck to regulate the flow of sand from one side of the glass to the other. Once fine-tuned, hourglasses can be used to measure a fixed amount of time. Finally, the candle clock, which dates back to as early as 500 AD, is a candle with consistently spaced markings that, when burned, indicate the passage of a certain period of time. In addition to these early timekeeping devices, calendar systems were used to measure the passage of time. The first evidence of lunar cycles being used as a dating system can be found around 32,000 BC. Today, the Chinese, Hebrew, and Islamic calendars still use lunar cycles. A solar calendar, on the other hand, uses the position of the sun for its dating system. The widely accepted Gregorian calendar is an example of a solar calendar. Jumping to much more modern times, the development of the mechanical clock, then the electric clock, and finally the atomic clock have drastically changed both the way we measure time and the accuracy of it. The first successful atomic clock was built by Louis Essen, an English physicist, in 1955. The clock worked by measuring the oscillations of a cesium atom and was accurate enough to redefine the standard unit of time. Before the atomic clock, the second, which is the SI unit for time, was defined by taking a fraction of one solar day. However, with this new accurate way of measuring time, the second was redefined in 1967 as 9,192,631,770 hertz, or cycles of radiation of the cesium atom. Modern-day atomic clocks are built and managed by the National Institute of Standards and Technology, or NIST for short. NIST currently operates 2 cesium fountain clocks called the F3 and the F4. These clocks are estimated to be accurate to the second after roughly 300 million years. Now, in 1905, a theoretical physicist named Albert Einstein published his theory of special relativity, and 10 years later, his theory of general relativity. Einstein's theory of special relativity describes how an object's speed affects measurements of time, space, and mass. His theory of general relativity, on the other hand, explains how gravity fits into the mix. Einstein's theories opened the door to a concept called time dilation. Time dilation is defined as the difference in elapsed time as measured by two clocks, either due to a relative velocity between them or a difference in gravitational potential between their locations. In theory, the faster an object moves, the slower time will pass for it, and vice versa. Additionally, the stronger the gravitational field, the slower time will pass. This concept presents a whole new way of looking at time. Rather than viewing time as a universal measurement that everyone and everything experiences simultaneously and equally, time in reality is experienced differently by each person. So in theory, if we took a rocket ship and put Sam on it, and sent him out into space traveling at 99% of the speed of light, or roughly 184,000 miles per second, and Sam spent 1 year in space traveling before he returned to Earth. When he returned, he would have only experienced 1 year's worth of time, but we would have experienced a little over 7 years, according to the math. Another example of time dilation can be seen in the popular movie Interstellar, released in 2014. This film, directed by Christopher Nolan, accurately depicts gravitational time dilation. When the main character, Joseph Cooper, played by Matthew McConaughey, and his team leave for their mission to find a new habitable planet, Cooper's daughter is only 10 years old. However, when he returns from his mission, she is aged more than Cooper to the point where she is physically and theoretically older than him. This is mainly due to the time dilation that Cooper experiences when he must travel close to a black hole. Black holes are regions of space-time where gravity is so strong that nothing, including light and other electromagnetic waves, can escape it. Per Einstein's theory of general relativity, Cooper would experience an extreme slowing of time compared to stationary observers, such as his daughter. Now, as with any theory, many physicists wanted to see if this was true. So that's why in 1971, Joseph Hafele, a physicist, and Richard Keating, an astronomer, took 4 cesium atomic clocks on board commercial airlines and flew twice around the world, first eastward and then westward. They then compared their clocks to clocks that had remained stationary. The sets of clocks were found to disagree with each other, with differences consistent with predictions of Einstein's theories. After traveling eastward, the clocks were shown to have slowed down 59 nanoseconds, and westward to have sped up 273 nanoseconds. Now, the change in nanoseconds of the clocks can seem very negligible in everyday life. However, time dilation has an impact on many things, including something that many of us use every day, the Global Positioning System, or GPS for short. The satellites used for GPS travel at about 17,000 miles per hour while orbiting Earth. The extreme speeds of the satellites lead to kinematic time dilation. Additionally, the satellites orbit at around 13,000 miles above the Earth's surface. The decreased gravitational field from this high altitude also leads to gravitational time dilation. Because of this, the clocks in the GPS satellites appear to run faster by about 45 microseconds per day than the clocks in GPS receivers on Earth. GPS satellites must adjust for this time dilation regularly in order to accurately report your location. Without proper adjustment, GPS will become inaccurate at a rate of about 6.5 miles per day. Finally, for my message to the senior class, no matter how much you experience time, time is a limiting factor in all of our lives. Whether it is the time left in each day, the time left in high school, or the time left in our lives. Remember to use your time that's left doing what you love. Thank you.
Evan, speaking as an English teacher, I think I understood some of that. I knew some of those words.